Have you ever had to consider in your network test setup what would happen if you put a tool into it, whether the time-sensitive network would continue to function, what aspects of that network the tool might need to be aware of, and what impacts it might have? That's really what I want to talk about today, and that's time-sensitive networking from a tools perspective. So the things that we need to think about to make sure that we can continue to test and simulate. I've split up the talk today into essentially 5 different areas. I want to go over a brief introduction to time-sensitive networking technologies and where they arise from, what the purposes of them are. For many of us, this will be a review, but it's a good baseline. And then I'll talk about timing synchronization, what that is, how it works, how it impacts our tools, queuing and shaping, how those interact. And then a brief overview of just a bit of an example of how this all comes together in the tools, and then I'll conclude with a few remarks. So first of all, I'd like to start with a small example with the network up on the right-hand side here, where I have just a very traditional solution. I have an Ethernet switch with 3 ports on it, a couple of cameras, and some sort of an ECU doing something with the data from those cameras. And those cameras are sending data, generally probably in a burst as frames come in. And that may result in oversubscription in the switch. When that happens in the switch, due to the uplink, the switch has a couple of choices. The first thing it can do is buffer packets so that we don't lose them, because we'd prefer not to lose packets. But eventually that buffer may run out and the switch may have to drop the packets. So then we end up with a little bit of burst interleaving on the output as the switch does its best to not lose anything. Those streams get spread out and we may get a little bit of loss. In Automotive Ethernet, that can be a real challenge because we may be bound by the electronics in the vehicle that we have. We may not have enough uplink bandwidth. And the bandwidth is there, it's just not allocated very well. So we could have a couple of real-time streams like this. They may be critical. We may not want to be dropping them. Generally, we don't want to drop them. And ideally, we want a predictable network, and ideally a network that we could actually make deterministic. And this is where time synchronization starts to come in. Within the standards and the technologies that we see, I'd really try and divide things into 2 areas. The first one I think of is time synchronization. So in order for anything to happen, we really need all the elements in the network to have a common understanding of time and a common time base. And that's where time synchronization comes in. So if you're hearing terms like IEEE 1588 or GPTP or IEEE 802.1as, we're generally talking just about synchronizing time in a network. The second area that we often see is queuing and shaping. And this is where we start to get into prioritizing traffic and scheduling traffic in the network and setting apart schedules. And of course, that is based upon having a common understanding of time. There's many options available here. On the next slide, I'll give you a very brief list of them. But a couple of the ones that you tend to see are basic VLAN priority, so where we'd pull a VLAN tag and a priority, determine that the traffic goes in a queue based on that. Or we may see some time-aware shaping and perhaps a credit-based shaper. And a credit-based shaper is perhaps trying to smooth out a bursty traffic into something more constant on the network. So common terms you might hear if somebody's talking about queuing and shaping could be VLAN priority, time-aware shaping, credit-based shaping, MSRP, which is a reservation protocol, or you may hear terms such as 802.1q, ... QBV, Q, etc. And these are the different shapers that have been defined. This is what I mean when I say there are a lot of standards, and I'm sure many of you have seen them. The 802.1as standards really relate to timing synchronization in the network. And AS Rev is I believe, just about done. 802.1q is the family of standards where we start talking about queuing and shaping. And there's many of them. I don't intend to go through them, but there are technologies that we do see talked about and perhaps applied. Some of them don't apply to Automotive Ethernet. Some of them do. There's many different application areas. So I'll talk for a moment about timing synchronization. So now, what it is and what the challenges are for a tool that's working in a network that is using timing synchronization. So if we take a step back to the example that we had before with the 3-port network switch or Ethernet switch that we had, the first step that we could take towards a solution is obviously to spread out those streams so that the cameras are maybe sending them at different times. And then we don't end up with congestion in the switch. So what we can do there is we need to synchronize our clocks, and we can use a protocol like IEEE 1588 for that, or GPTP. At that point, everybody has a common understanding of time, and we can tell camera 1 send at time X and camera 2 at time Y, and then the switch will put those together nicely for us. We don't end up with any queuing, no latency variation, no loss. Things work very nicely. So it's a very simple solution to the problem, and can solve some issues. I took just a very simple setup, very simple switch evaluation platform, and ran a simple test on it. I just took 2 streams that were overlapping with each other with a iMix of traffic on them, which is a mix of different lengths of packets, and sent them through the switch where I knew that they were going to collide with each other at the egress port. And what I saw as I increased the rate is about a 30 microsecond latency. Of course, that depends very heavily on the uplink rate as well as the amount of buffer in the switch, but in this case about that, and about a 0.5% packet loss. So I could just see it starting to taper off in terms of switch performance. By doing a little bit of simple traffic scheduling, like on the diagram I showed before, just separating those 2 streams from each other so they were no longer overlapping, my latency variation came down to 2 microseconds, it's not variation, the latency as a whole, which is essentially the store and forward latency through the switch. So I know I'm not buffering anymore, still have the same throughput though. And my packet loss was totally eliminated. So sounds like a great solution. We've gone partway towards the problem of making our network more reliable. Now, if we go back to that example again and say, well, I need to simulate that switch because maybe it's not available, and we need to use a tool for that. In this case, I've taken a tool and said, this is perhaps one of our tools. Well, what does that tool need to do in order to continue to work? Well, the first thing is that those 3 endpoints that are doing timing synchronization need to continue to be able to synchronize time. And that's critical. The challenge is that the latencies through the switch do vary depending on blocking, and we need to make sure that that continues to work. In the absence of putting the master clock in the switch to provide that, one of the solutions is to use what's called a transparent clock, which is defined in the 2nd version of the 1588 spec. And essentially what the transparent clock and the switch will do is update the latency values as they pass through in the adjustment field of the 1588 frames. So in this sort of a scenario, in this very simple scenario, what the tool needs to do is implement a transparent clock, and the endpoints can continue to synchronize to each other, and the network will continue to work. But of course, nothing's that simple. So then we end up with queuing and shaping. So queuing and shaping is really about the solution where I maybe have stream A and stream B, like we had before, and then there's some other low priority traffic that comes in. At that point, we've lost control of what the switch is going to do. Because the switch might be able to prioritize A and B, but the low priority stuff can get mixed in too, and then our latency goes sideways on us, and we may end up with loss. So really, it's when that non-time aware or non-scheduled traffic comes into the network that we need to talk about, well, how do we solve this with queuing and shaping? So when you add queuing and shaping to a network, what you're adding is time awareness in the switch. So the switch now needs to be aware of time as well. It may have a slave clock. It does not necessarily need to be the master clock. And the switch will implement some form of queuing and shaping. That could be as simple as a VLAN priority or as complex as a credit-based or time-aware shaper, depending on the application. And what we see then is that the switch can now put those packets on the line at the right time, and we get a very low and constant latency through the switch with very little variation. It makes the network a lot more deterministic. And the non-time aware traffic is going to go and fill in the gaps for us. We essentially aren't going to have any loss as long as we're not oversubscribing the line. It's generally going to work fine. If I look at that from a tool perspective again, we have a couple of challenges. The first one is now The tool also needs to have a sense of time. So I need to have a time base in the tool that is synchronized to the network. The tool also then needs to start identifying and prioritizing the traffic, and how that's done depends largely on the customer application that is being used. It may be as simple as VLAN priorities, but there could be something more complex going on as well. So we also need to start being aware of that. And then the switch also needs to implement some sort of queuing or shaping mechanism. Now that could be as simple, as I said, as a VLAN queuing or time-aware shaping or credit-based shaping, and it just depends on what's going on. And then the other challenge that we face with the tool is, well, how do we configure it? How does the customer configure that and make it match the simulated network without being overly complex? So now I'd like to look at that all in the case of maybe a complete example where we have timing and sync and queuing. So as I said, TSN, the family of standards defines a large variety of scheduler and shaping solutions. And the target markets for that family are broad. We have Automotive Ethernet, Industrial Ethernet, the Pro AV teams use it, and there's many others as well. And our challenge is to, I think, distill that down to the tools and the standards that our customers need without making the tool overly costly or complex. To basically distill it, if you will. So in that sense, I've picked out 4 technologies that I think are worthwhile talking about a little bit more. The first one is 802.1as, the IEEE standard for timing and synchronization. And the 2 things that I think we need to think about here from a tool perspective, as I mentioned earlier, are transparent clocks in the tool. So you know when you put the tool in your network that it's going to work. You're not going to break your network. And the second one would be boundary clocks, allowing the tool to be a clock, either a master or a slave. Second one would be VLAN priority queuing. So this is the most basic form of prioritization in the network, where we might have 8 queues available or 2 depending on the configuration, and we would use the priority in the VLAN tags of the packets coming in. Here we can have more reliability, and in a simple network it's definitely adequate, but as you end up running across multiple hops in your network, the VLAN priority queuing starts to break down. That's where we start to get into time-aware shaping. Time-aware shaping is advantageous because then or time-aware scheduling shaping, because what happens there is that then if I have 6 switches that are cascaded after another, I can ensure that when my packet enters the first switch, by the time it leaves, the second switch has the gate open and that packet's going to flow straight through the network. So I eliminate jitter and buffering through the network. So we see this as another technology that can be very advantageous. And then the final one is a credit-based shaper, and that's perhaps in a tool application less interesting. A credit-based shaper might be something that smooths out the bit rate from a camera, for example, and creates a constant data rate. But this is something that could also help in avoiding frame loss because you avoid the burstability. So if we take those and look at an example, back to our simple network that we have, where I have 2 cameras and a switch in the network and an ECU attached to it. And perhaps my measurement setup having some sort of an issue or some hardware is not available, I said, well, I'd like to record the camera data from one of the cameras, so I'd like to send that to a logger while not disturbing the network and see what's happening. I may need to simulate the switch because the switch hardware is not there. So we'll simulate the switch. And I'd like to simulate that ECU as well because it's also not available. So I'm going to have to connect Canoe to it. So this creates some challenges for the tool. So if I put those inside of one of our tools, then there are 3 different types of connection that we would use. If you will, PHY connection or interfaces. The first one is a PHY tap. It's basically at the electrical level of the PHY, we're going to pick the signal up and send it back out again on the wire, and that allows us to record the camera data as well as send it off to a logging port. The second type of connection is a direct connection, and a direct connection is essentially the ability for Canoe to come into the network and act as though it's part of the network. So we're going to use that to connect the Canoe simulation of the ECU onto the network switch. And then we're going to have a switch connection as well. And in this case, we're going to have a 3-port switch. And that's going to allow all of those devices to connect together. And they'll all be able to talk to each other at wire speed. So the challenges that we have when we do that, and how that implies, or how that impacts the tool. For the PHY tap, there's actually not much that happens in terms of time-sensitive networking. The latency through the PHY tap is essentially fixed. We have to do a little bit of interframe gap adjustment, but it's very small. So your time sync will continue to run across the tap without issue. Essentially transparent in the test setup. The direct connection is a little more complicated. The hardware needs to provide transmit and receive timestamps of the packets as they enter and exit the real network. And by doing so, they allow the software that's running in the simulated environment to maintain synchronization with the real-time world that's happening underneath. So we get that virtual to hardware world connection. And then the switch, as we've talked about, becomes slightly more complicated. So the switch, we want to look at transparent clocks for the cameras, perhaps, to maintain synchronization. Boundary clocks if need be. So if, for example, you were simulating the boundary clock as well, then we would have to think about how that works. And then we also have to think about queuing and shaping in the switch. And whether we support the standards that are needed. So when you're replacing a switch from an OEM in a network, we have to think about, how do we mirror the functionality that was in there into the switch that we have available. And that, the actual implementation of that may or may not be required, and it may not be required that it be fully compliant with the standard. It might be something that we can mimic, if you will. So these are the types of things that we want to think about when we are replacing real hardware with tools. So I'll summarize that all back together again in a conclusion. So I think the major points for us, or for me, when I think about tools and time-sensitive networks, are picking the right standards that we need to support, and then distilling them down to really what we're trying to do with the tool. We're not necessarily trying to test the whole standard, but we're trying to use the standard as an enabler to have the tool in the network, and we don't want to disturb the functioning of the standard. I think secondly, it's incredibly important for the tool to be transparent in the network, as transparent as possible. So we'd like not to disturb the real setup when you have to insert a tool. And where there are impacts, we'd like to make sure that those are well understood for the customers. The next thing is that the tool also needs to work between the simulated and the real world, if you will, the standalone world where the tool might be sitting in a network without software. And so we need to create the connectivity between simulated time and real time. And so that's something we have to be very careful of when we're designing tools and designing interfaces into real-time, time-sensitive networks. And then the next point is configuration and complexity. The standards are incredibly complex. There's hundreds of parameters to configure for these elements. And we need to find a way to provide the ones that are critical and provide as much automatic configuration as possible while not becoming overly complicated and unusable. So we want to make sure we have the right use cases, that we understand the right use cases, and we're able to solve those. And then the final point, especially being a developer myself, is tracing and debugging. We know to think very hard about how do we look at issues when they occur in the network. If I'm ending up with a buffer overflow or dropped packets, what are the things that the tool can do to provide better traceability and debuggability to make that easier? So that's the final aspect of things that we think are important. With that, some questions.